because again, we've done a lot of optimization to try to make sure that the other models we compare to are presented in as good a light as possible. And we are winning by some 10 map when we actually fairly measure everything.
Hello, everyone. Welcome to Roboflow's weekly webinar. This week, we will be talking about RF-DETR and RF-DETR segmentation, our new state-of-the-art model for instance segmentation, real time. Today, we have a very special edition with two machine learning engineers for our team, Matvei and Isaac. A couple things before we get started, and I pass off to Patrick, who'll be helping moderate. Please stay on mute throughout the session. If you have questions, feel free to put them in the chat. I'll make sure that all of them are read. And toward the end, we'll have a time for Q&A. And we've already got a few pre-prepared too. So thank you for everyone who submitted those. Stay on mute. If you have questions, put them in the chat. And we will also record the presentation and put it on YouTube. So if you do want to refer back to it later, we'll have that as a resource. And with that said, Patrick, let's begin.
All right, let's get started. On the screen here, you see some beautiful computer vision output examples that feature a new instant segmentation model. And today we are going to be interviewing two of the main contributors to the project that resulted in having the model that is behind the imagery that you see on the screen. During this session, we're going to be diving into RF-DETR, what it is, what some of the capabilities are, and learning a little bit about some of the recent additions to this model. My name's Patrick, and I have with me two of the, as I mentioned, contributors to this project. And how about we get to know them very briefly? Isaac, would you like to say hi to everybody?
Hello. Very excited to talk about this model.
Wonderful. And Matvei, would you like to say hi?
Yeah, hi everyone. Me and Isaac here, both from the Roboflow models team. Super excited to meet you and talk to you.
All right. Let's dive into the content today. So we're going to have a sort of quick introduction to RF-DETR, kind of what it is if you aren't really familiar with this model. We're going to take a look at some benchmarking. And then we also have some questions and also some projects that were shared by some of the audience members today. And we'll be reviewing some of those later on in the session. To get started, RF-DETR, Isaac, could you let me know if I've never heard of RF-DETR before? What is this? What does it do? Why are there so many letters in this acronym?
Yeah. So RF-DETR, Roboflow Detection Transformer, is a new model in the line of work of DETRs, which are object detectors based on this idea of a backbone and then a transformer-esque cross attention to the backbone feature space such that you produce objects. This notably deviates from the YOLO framework, where you do not have this cross attend and you simply have a backbone that in one stage produces predictions. The fact that we do this cross attend allows us to have some very interesting properties. For example, we do not need to run non-maximal suppression after processing the image, which reduces runtime and also allows us to handle more aggressive overlap between objects. The naming convention for DETR series models tends to be abbreviation dash DETR. In YOLO series models, it tends to be YOLO V blank. So there are a lot of letters on the screen just because we borrowed from the same naming convention that all our predecessors did. Apologies for the acronym soup.
Now, there's been some improvements over time since the initial release of RF-DETR. I think the original object detection models came out in March. Since then, you guys have been busy with other releases. Another notable release was a couple months ago where there were some new checkpoints, new sizes, and then some improvements to performance. And then today we got together to have this session because I think it was just last week that the RF-DETR segmentation preview was released. Matvei, could you give me a quick introduction to what the news was last week?
Yeah, so we basically released a preview of RF-DETR Segmentation, which is the instant segmentation model that you mentioned, Patrick. And it's available to be trained in Roboflow platform, as well as in our open source package, and in our inference package. So it is basically widely accessible across all ways to train and run model that Roboflow offers. Yeah, and that's kind of the thing that is out so far.
Nice. If I'm interested, you mentioned it's generally available. Just real quick, if I'm interested in testing it out, where should I go to do that?
Yeah, so you should probably go to the Roboflow platform, and if you have a data set already, that's great. But if not, we can help you super quickly assemble one, label them super quickly, or you can just upload it. And you can just, with the minimum amount of effort, just hit off a train button, just literally click it, and it's gonna train the model for you. And then the next button you'd click is deploy, or just like run a workflow with inference of RF-DETR Seg, and it is gonna once again do it for you, show you the results, how it works, and everything like that. So you can inference it there as well. So I would start with that, and if you want more customization and things like that, you can check out the open source repo and to get more familiar with the model as well, with the link that James shared in chat.
Moving on, I wanted to take a quick look at some of the benchmarking results that we compiled along with this release recently. And just to help people understand what we're looking at here, we have this comparison chart that we're going to look at that has on one side accuracy, and then down below we have latency. And with these kinds of charts, usually referred to as Pareto charts, you want to see some data points that are typically in the upper left side, as that would indicate that you have a better mixture of accuracy and latency. So generally, kind of the higher you are up in that quadrant, the better performance is. So for example, with YOLO V8, according to these benchmarking results, you can see there's a couple different data points of the different model sizes. And then, for example, YOLO V11, it improved upon the performance of that model. As you can see, some of the data points here at lower latency, they have slightly better MAP accuracy scores. And then last week, what was released was the benchmarking for the RF-DETR model, which you can see is a sort of significant jump toward that upper left portion of the screen. Isaac, could you tell us a little bit about what we're looking at here?
Yeah, so there are a couple interesting things. First quick note is that this is a preview of our ultimate RF-DETR segmentation model. It worked well enough. We're doing a large pre-training of it, and we tested it on a downstream transfer, and it worked well enough that we figured we'd release it and start eliciting feedback from the public before we proceed with the rest of the training. So interacting with you all is super, super helpful for us. So again, this is a preview. That is why the curve stops. The ultimate one will keep going and be just a little higher than this. So the major thing happening here is that we're testing latency and accuracy for different model sizes and different model families. There's an important note to be made that many people in the research community, when they benchmark their models, they report accuracy with float 32 and latency with float 16. They'll also do things like run one type of NMS during evaluation and another type of NMS during prediction, or they won't include NMS as part of the runtime. All these different inconsistencies with how we measure models, which can lead to inconsistent conclusions about performance. So as part of our work for RF-DETR, we wanted to ensure that we are measuring things in a way that is both fair and reproducible. So notably, RF-DETR does not require non-maximal suppression, does not require, it gives you masks for the objects just from running the model. You don't have to do any complex post-processing. The Ultralytics models do require non-maximal suppression. They do require converting the prototype masks into objects masks as a post-processing step, and that's expensive. So one thing we do when we're benchmarking these models is we actually, we want to steel man the other models. So we did work to optimize running a YOLO end-to-end with NMS and mask generation fused all into TensorRT. So we built some new tooling to do that. We also wanted to make sure that some models get worse when you run them in FP16. So we wanted to make sure that a point on the chart here is actually attainable. You get both the latency and accuracy when you run the model on hardware. So these numbers are the YOLO numbers are a little bit lower accuracy. Some of them are faster than reported. Some of them are slower than reported because, again, we've done a lot of optimization to try to make sure that the other models we compare to are presented in as good a light as possible. And we are winning by some 10 map when we actually fairly measure everything to the best of our ability. So we feel quite good about how this turned out, and we're very excited about how the non-preview version will perform compared to state of the art.
Beautiful, thank you. Yeah, I had actually prepared my next question here, which is also, just for my own benefit or anybody else who might not be familiar with reading these charts. So if we take a look here, what I have on the screen now, at the kind of like the smallest to the fastest data point that we have for each of these models, all of them are running like below or measure that below the 4 milliseconds of latency. And then we compare that YOLO V11 and it was around 30 MAP. And then the RF-DETR segment preview was, I think, 39.4 perhaps was the MAP. So there's a 9.4 MAP improvement here. I do have a question, I guess, that I'll toss at either of you, which is, what does this, I guess, maybe mean, or what do you think people should take away from seeing this screenshot of this benchmarking result? I guess from a software development point of view, perhaps one way to think about it is, well, for the same latency, for the same cost, I'm going to have a much more accurate model. Matvei, I see you nodding your head. Do you have some kind of thoughts about the real world implications? Why should this excite people?
Yeah, I mean, basically, you actually, if you look at latency, it's even a little bit faster. No, for a slightly
Fair point.
So you get better accuracy for a faster runtime. So you really could not go wrong with that choice here. I think for me, it really just showcases to like how much benefit we're getting here from the pre-trained backbones and just like having transformers in there as well. I think that's a big thing for people to realize. So that also just kind of tells you, as a like usually models are measured on Coco, all of their performance, which is what we're seeing here. But as a customer, you care about just as an engineer, you care about a data set of your own where you want to have a good performance, which might not be necessarily reflected in Coco score. But with RF-DETR, there is not a score here on 100 VL, but that's another thing. We have a data set that shows its transferability to different custom data sets. And there's like a similar story over there. And you can be more sure that's for detection, but overall the same story is because we use these pre-trained backbones, you could be more confident in terms of the model transferring on your data set with your custom use case to perform better. I think that's kind of like the biggest story and takeaway from me here.
There's one additional thing which I don't think we've made super clear to the community, which is this curve for RF-DETR. This is actually one checkpoint run at 3 different resolutions. We're generating this Pareto curve. It's literally the same weights, you're just running them at different size images. Whereas all of these other points are different architectures for different latencies. It makes the deployment much, much, much more flexible. Because you can choose what latency you would like to run it at after you've trained it.
Yeah. That's a great point. So it is important to keep in mind, right, that if you are to change your resolution, you will probably, like, if it goes up, you will probably see a better performance, but also do expect the latency to go up. And it is the same model that we released, as Isaac mentioned. So that's kind of a very important thing to emphasize for sure.
Nice, cool. Yeah, I think actually we have some questions later on where we could swing back around to that topic. For now, I'd like to actually start taking a look at some of those questions and some really exciting, cool projects that I've seen from the community. So before this session, I asked registrants if they had some questions about RF-DETR in general, or if they had used RF-DETR in any of their computer vision projects, and got some cool responses from people. So some of these questions you'll see in some of the projects, they might not be specific to today's topic about instance segmentation, although perhaps when we're discussing some of them, we may even feel like perhaps we should try retraining or testing out some things when it comes to segmentation. Before we get started with those questions from the audience, I personally have a question for all of you here today about the pronunciation of this acronym DETR. I would really love it if in the chat right now, everybody could let me know about how you were previously or usually say this acronym. If you, I have three options here. One is A, the short E. You say it kind of as a word, RF-DETR, as I think maybe the three of us have been saying it on this call so far. B, you say it as a word, but with a long E, RF-DETR, I've heard some people say. Or do you spell out this acronym, RF-DETR? So in the chat right now, I would really love to see the results of this. I don't know if we're going to calculate this. Maybe James and I could calculate this and come back to the answer at the end. Or James, actually, do you already have the answer?
Yeah, I've got the answer. It's a resounding A, RF-DETR. So I think we can finally put to rest that discussion internally about how do we use this. So let's start using RF-DETR.
I may have been inspired by some internal discussions I saw at a meeting yesterday, and now we have all the ammunition we need to go back and close those ones. All right, so let's move on to take a look at a couple projects that were submitted to us by the audience, and we got a really cool one here from somebody named, I think it's Ahmad, perhaps.
Sure. Yeah, I'm Ahmed. I work at Interpro Pipe and Steel in Regina, Saskatchewan. We've been working with Roboflow for a few months now. Our challenge is to detect hazardous or undesirable material in our incoming scrap. So we get about 3,000 of these pictures per day that we want to eventually analyze and flag for bad things. It's a difficult problem because our scrap is random, as you can see in this picture. It's somebody else's garbage. And each piece is in a random orientation and it's on a background of more random garbage. So far, we've annotated a few thousand images with 10 to 20 annotations per image. And we found that with the RF-DETR, if that's how we want to pronounce it, that I think it was quite a bit better than the previous Roboflow model, with much more usable output with a similar number of images.
Could you tell us a little bit more about this project? I really love it. What is maybe perhaps what's the kind of like the action or the insight that you're hoping to draw from this model? It sounds a little bit like if you identify something that should not be in the scrap, you'll probably want to remove that. Is that correct?
Yeah, so this is the last point of inspection before it goes into our furnace to be melted. We have a large overhead crane that use a magnet to load the scrap into a big bucket, and this is a picture in that bucket. So every time they drop something, we take a picture. The idea is if we see something that's absolutely shouldn't be there, we'll stop their process and tell them to take it out. if it's something that's non-injurious to the process, we can use it to train our other models, which predict the chemistry and other performance of the steel.
Wow. Wow. Okay. Nice. This it kind of reminds me of some other projects I've seen that were about, I'd say, kind of reducing some waste and kind of like finding other use cases for like remaining kind of scraps, stuff like that. Besides kind of like avoiding items going into the furnace, is there kind of like anything that you can do with these objects, put them in a different process, recycling, anything like that?
Well, we are the recycling process, so we're taking everybody else's garbage and we're trying to make it into steel again.
Oh, nice. Cool. All right. Well, about the model, do you have any sort of like questions, things like that for us?
No, I'm looking forward to the segmentation, or the segmentation, the next preview one. We actually annotated all of our images with polygons because we're hoping to do segmentation eventually. So I think we're ready for that.
Beautiful. Thanks. That was actually going to be my last question. I showed this image to, I think, James before we started, and immediately he was like, let's try segmentation on that. So thank you very much for sharing your use case. If you have any other questions about that, feel free to let me know. And really excited to see how things go with the segmentation model. We have another project that was submitted ahead of the call, and I think this one came from Niels. Do we still have Niels on the call? If so, it would be great if you could unmute yourself and let us know a little bit about what's going on.
Yeah, sure. Good afternoon, everyone. Yeah, first of all, thanks for your great work because the Python package is extremely user-friendly. So for my master thesis, I worked on quite an interesting problem. So at security checkpoints, for example, at court, you have to deposit certain items in a tray, like a watch and a belt. And currently, security personnel just instructs those people on what to deposit. It's quite repetitive work because they have to often repeat the same instructions, and people do not always listen. So the question was like, hey, is it possible to partially automate this process? But as you might know, occlusion is quite an issue for accessories, as in winter, a watch is often occluded by sweaters or even a jacket. So therefore, the model also needed to be quite robust to occlusion. And we also wanted to benchmark it. So we created a new data set that both has clothes and accessories with occlusion level annotations. And then we trained RF-DETR and also some other models on the Fashionpedia dataset, and we evaluated it on the Fashionpedia test dataset, and also then our newly created Fashionville dataset that has occlusion level annotations. And then what was really interesting to see is that the performance of the RF-DETR base and also the RF-DETR large model was way better on the Fashionville dataset when they were all trained on the Fashionpedia dataset, which shows some kind of within domain generalization, as the images in the Fashionpedia dataset are more at places like a catwalk, while in the Fashionville dataset, all kinds of people in an inside environment. So it was quite cool to see. And this might also, this is also something that you try to showcase, I believe, with the RF 100 VL benchmark dataset. And then we also benchmarked several of these models and also RF-DETR on different levels of occlusion. And you can see it in figure 12. And what you can see there is that when occlusion increases, the performance of models approximately degrade at the same rate, but the best model still remains the best. And then lastly, we also converted the RF-DETR model to TensorRT, which was also really easy to do with your Python package. And then we deployed the model on a Jetson or a Nano, and we added a graphical user interface that shows those people at security checkpoints what they have to do, and then they see an icon that text like, hey, do this or do that. And now, we're also looking at moving this proof of concept setup to a minimal viable product, and we are considering using Roboflow for your pipeline, and then especially for edge device deployment and monitoring. And also working on a publication, but that's more focused on the data set of this project. So that's it from my side.
Wow, thank you so much for that introduction and sharing your project. Before we get on to the serious questions, man, Fashionpedia, I feel like I should probably go check that out sometime. I think I could learn a thing or two. Niels, you had a couple questions that you had submitted, and I was actually hoping that the team, we could help talk about these a little bit. I think the first one that you had submitted ahead of time was about the domain generalizability of RF-DETR. Isaac, Matvei, would either of you want to talk a little bit about this? I see Isaac raising his hand.
Yeah. So just I think it's important to say high level that our goal with this work wasn't to win on Cocoa. It was to make something that generalizes as well as possible. And turns out we also win on Cocoa, which is very convenient for us. So the core trick is basically, we tried to build models that were amenable to use via large pre-trained foundation models, which is a real challenge because people don't build foundation models that are at the level of latency that we require to be like this nano or small scale. So that's why our initial release was the base, which is similar to like a medium latency because that's the fastest we could get with traditional foundation model. But so yeah, big goal is to use the foundation model. Another big goal is how do we preserve the knowledge of the foundation model while doing additional pre-training? And the major statement there is just significantly reduced learning rate and aggressive learning rate decay per layer learning rate decay in the backbone, which hurts performance on Cocoa. But again, our goal is not winning on Cocoa. Our goal is something that generalizes super well, that has the type of properties that you talked about. And we went on Cocoa anyway, so it doesn't really matter. There are a lot of other tricks that go into it that will be, we're releasing a paper soon. We're working very, very, very hard to get it out. There's a lot of stuff to talk about. So we're trying to make sure that we're communicating clearly and including enough experiments such that people understand what it is that we are doing and attempting to do. So I cannot talk about kind of the further tricks that are, I think, very pretty, but the core statement is, a core statement is very nicely pre-trained backbone, and how do we make sure we're not erasing that knowledge while we do object detection pre-training?
Cool.
Does that answer your question?
Yes, thank you. That answers my question, and it's quite interesting. That works really well. Yeah.
Nice. Niels had another question too about do you know whether using Sahi in combination with RF-DETR can improve that occluded object detection? Is there anything that Matvei, Isaac, you could share about that?
I think you should just go ahead. I think you have a lot of thoughts on it.
Okay, cool. Yeah, so I don't think Sahi by itself gives you that much. I think the big thing that one can get is just running higher resolution. If you have a fixed image and you run that image at a higher resolution, it is easier to see the boundaries between occluded objects, and so you can get better results. So if running Sahi means that instead of running the whole image at a fixed resolution, you run each crop at that same fixed resolution, then you are effectively blowing it up and you get potentially better performance on occlusion. But other than that, it's not really clear to me that there would be a mechanism. I don't see anything specific with Sahi that would be super useful because Sahi is about stitching together things as you run through multiple crops, and I'm not sure why the stitching would help.
But I'm assuming you're open to being proven wrong if somebody can show you.
Very, 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 very open to I would love to be proven wrong. Whenever I'm proven wrong, that means there's something that I can do better. And when we do better, we get better for everyone. So I'm very excited.
Beautiful. All right. And then there's going to be there's sort of a couple questions, and we already addressed this a little bit, but maybe I'll just put Matvei on the spot for this one. But let's talk a little bit about that final question about resolution, improving model performance. Could you talk a little bit about that, Matvei?
Yeah. So basically, just coming back to Isaac's point from before, the key difference between all the RF-DETR family models and other models that are out there in our graphs is that technically RF-DETR models are all sort of the same model weights and architecture, and we are using different number of parameters in this architecture. So we're like having different number of decoder layers, patch size, and things like that, as well as resolution. And so you definitely would get a higher performance, increasing the resolution of the model. But you are kind of moving away from that set point on the graph that we have established, and you're going kind of up towards the larger family of the model. So your latency is also expected to go up. And that's an important thing to consider. If latency is not an issue, then totally go all for it. You can get a higher resolution. The only thing to mention is these models do, like if you run them in their original setting, I imagine this is a pretty reliable standard result during pre-training that we had. So there might be some instabilities when you change that. But I wouldn't be too concerned about that. So if it works, it works. Yeah.
Beautiful. All right. Niels, does that help with all of your questions so far?
Yes, thank you. Can I maybe ask Ace or make a small comment or something that I noticed when testing this in real life is that when the context is missing, so if you want to detect a watch but you only have the arm in the image, it is harder for the model to detect the watch compared to when you see the whole body for the model. That's something that I noticed, yeah, which makes sense with the attention mechanism. I believe that is that's something we noticed when testing it.
Perhaps you could, if you could, you already have my email. Perhaps you could email me a couple examples of that, and if we have some time, we could also look at it as well.
Yeah, sure.
Beautiful. All right, thank you so much for sharing your. Oh yeah, sorry.
Yeah, sorry, but before we move on, since Sahi came up, a lot of people in the chat have been asking just generally about how RF-DETR performs on small objects, both natively and with Sahi. I'm curious, Matvei, Isaac, if we've done any benchmarking on small objects, or whether we have any intuition about that, and whether Sahi is necessary, still helpful in RF-DETR. Just a quick overview while we're still on this topic of Sahi.
Yeah, Isaac mentioned this in the chat that like for YOLO specifically, we outperform on all sizes, which includes a small. But I think the thing to say is we have a paper that we're actively working on, which has comparisons based on all sizes, large, medium, small, and a lot more, and on different data sets. And so, yeah, I think basically just stay tuned for that. I think we'll have this out shortly.
Sounds good. In that case, then, I think, again, in the chat, we've been talking about just try RF-DETR segmentation on your data set and see how it performs. And if you see something where you're like, it should be better here, let us know. Or if it's great, also let us know. Yeah, thank you, Patrick.
Thank you, James. At the moment, I only see there's a little 99 plus icon for the chat right now since I'm sharing my screen. So thank you for jumping in and helping out with that. There was another question that we got ahead of time, and we might not have Eric with us, but to summarize, Eric was working on a project, and he mentioned he trained with RF-DETR, and I guess this kind of boils down to, his source imagery and imagery that he was using to test is 16:9 ratio, 1080p. And then when he was training, resizing it to 640 by 640. And then he had some questions. I think this was related to like a basketball use case. And he was thinking about, the basketball is round in my original footage. And then when I resize it, it's not round anymore. What's up with resizing and stretching and training versus getting that into testing and production? Isaac, could you tell me a little bit about this? Do you have any sort of guidance to provide when people have questions about resizing, changing ratios, things like that?
Yeah, I mean, the general knowledge, knowledge is the wrong statement. The general framework from my perspective is that the closer your train time data is to your inference / production / test time data, the better you're going to do. So here you have well, the RF-DETR has this little quirk where we assume that images are square. And there's some interesting technical reasons why that assumption may be a little more challenging to change than one would assume. So it's something to explore. But
I'll look forward to the paper on that.
Yeah, I don't think we're gonna have space to get into the paper, but that's something we probably will get into in the open source repo. God, this is so interesting. So it assumes a stretch resize to a square, and the 4x3 image, if you're stretching it, if you have like a round ball, the stretch thing will have a certain like ratio proportion. And if you then at test time have a 16:9, it stretches very differently. Now instead of like, like 30% wider, it's like almost like twice as wide. So that's introducing a train test discrepancy, and one can there's a risk that you will start to see a reduced performance. So I think any type of gap like that has the risk of introducing specialization to the train data that doesn't transfer to the test data. And this is, I think, a great example of where that could be happening. And you just got to be very, 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 very careful with model development so you don't get stuck on things like this. I mean, even literally like changing the camera can introduce train test gaps for very specialized models. Yeah, is there more?
I think that helps me. And I think actually what I've discovered is there's probably a webinar topic for me and James to tackle in the future. Cool. I think I might have one more slide. That there was a lot of questions that we had related to kind of like deployment, especially on perhaps like lower powered devices. But just like from a really high level point of view, Isaac, Matvei, do you have any kind of thoughts about using RF-DETR on mobile devices like iOS or Android? Any recommendations for people who might be interested in that?
Well, it's certainly one thing that we are working on actively right now. There is exports to CoreML in the platform available currently to run on iOS devices. We also have inference.js for web, but that's not as related. Yeah, so I think if you do want to export RF-DETR to work with CoreML and like run it on your device, I would do that via the path of the platform. That's like one of the features that we offer there. So yeah, I think just give it a shot, see if that works. That's something that we're currently working on, so there could be some hiccups there. So please reach out to us and we'll work with you on fixing that. I think as Christoph did, so I think get back to him on doing that. But yeah, that's definitely something that's being worked on, and excited to see how that turns out.
We have demonstrated running RF-DETR Nano, for example, at 120 FPS on an iPhone 16. So
yeah,
it's doable. It works very well. there is infrastructure available on platform to just do it natively, and we will be expanding the target hardwares.
That's a secret fact from the paper.
Yeah, if you go to Google and search for Roboflow iOS SDK, then you'll be able to learn a bit more about our iOS deployment offerings. And fun fact, if you train RF-DETR weights using the open source repo, then upload them into Roboflow, then you should then be able to, we'll handle like the export to core ML stuff in the background when you're using our SDK. And similarly for web, as Isaac and Matvei mentioned, search for Roboflow inference.js, and we're working on RF-DETR models for the web.
So that concludes some of the questions that we got ahead of time. I haven't had the chance to peek at some additional audience questions. James, do you have some other sort of like high-level questions that you think that we should be trying to address on this call before we wrap up?
Yeah, absolutely. So I'll kind of go through these quickly. We don't have to go too deep. We did have one on intuition, and I think Isaac has talked a bit about this, but it'd be great to get on the call of kind of using RF-DETR when you want to do object tracking and its reliability for that. We do have a lot of people interested in object tracking, and there are techniques for like detection smoothing and all these things. Isaac, Matvei, have you done any object tracking with RF-DETR models, with RF-DETR segmentation even, or any guidance just to point people in the right direction there?
Since Matvei did not immediately speak up, I can talk a bit. So we're researchers, and we have a habit of not actually ever viewing the output of our models until we have to share it publicly. So RF-DETR, we didn't see any boxes from it until after we released it and people started showing us that it worked well. It was very funny. Same thing with the segmentation model. Like, it was live before. No, that one we saw masks like a couple hours beforehand, like before we got it live. So that was a huge.
We did see the masks.
Yeah, that was a huge boon. But for tracking, we have someone in our organization, Piotr, who does a lot of tracking work, and he's released video tracking based on RF-DETR, especially versus like YOLO models. And there's this interesting because we hadn't tested this, we hadn't observed this ahead of time. When we first did the RF-DETR release, people were talking about like a buttery smooth like tracking was working very, very well. And the segmentation seems to have a similar thing. He has this video of people playing tag and getting like these nice track segmentations. And I think the big thing that's happening is that DETRs don't use non-maximal suppression. Non-maximal suppression has the property that you have many, many boxes predicted for the same object, and it's trying to select the best one. And little jitters on that confidence can cause different boxes to be selected between very, very similar frames, leading to jitter in the box. So the tracking itself gets a little bit more noisy versus it. This is at least my thesis as to why this is happening. I think the NMS it introduces a little jitter that is not observed in non-NMS based methods.
Jitter in the box is going to be the next dancing fad on TikTok, I think. We're going to start that.
Amazing. I really appreciate that direction. I think we can take one or two more questions, then do a wrap up. We do have one from Zach in the chat here, who's talking about our chart earlier showing RF-DETR compared to some of the predecessor comparable models for segmentation. Thank you, Patrick. And he was talking about kind of the really low latency that we're observing relative to the high accuracy. And Zach was curious about, are there real world examples? And maybe Patrick, you've seen some of these two working for our customers, of people who are really needing these really, really fast models. As Zach asked about, is it like useful for working on really fast conveyor belts? Or are there other use cases where like, now that we're getting these really, really low latencies, where that's like unlocking new capabilities?
Oh man, a question for me? I thought I was just going to be asking the questions today. Well, I have two things that come to mind when I look at improvements to accuracy. And the first thing is, well, both of them are related to, what model accuracy means to you in different situations. If you actually go to the Roboflow YouTube channel right now, a few weeks ago, I had a really nice chat with Sean from a company that works on a product called Almond Bot, which is they're using computer vision to teach. I don't want to anthropomorphize it too much, but to allow robotic arms to handle more complex tasks. So, for example, you have these different shaped sheets of metal that are piled on top of each other in a bin, and you need the robot to identify which piece of sheet metal is on top, where the center of that piece of sheet metal is, and then pick it up and then put it into the right bin. When I asked him about accuracy related to RF-DETR, because they are using an RF-DETR object detection model in that pipeline for their robotics use case, his answer was, in robotics, we're competing with humans. And he said, humans 100% of the time will succeed at picking up the piece of sheet metal. My response was, he should test me on that. We'll see if I can get it 100 out of 100 times picking up the sheet metal. But yeah, so he said, any improvement that we can see in accuracy to get as close to 100% is really important. Also, if you think about with robotics, there's a safety element as well, where you need to make sure that we're not causing any kind of accident, not causing any kind of damage, things like that. And then completely on the other side of that, when I think about what does accuracy mean to you, I think about situations where, especially in manufacturing, there may be a process that happens at a really high speed, and it's too fast for humans to process and catch an error in time. If we have 1,000 products going by on a conveyor belt each minute, each hour, let's think about, food processing. If you have the wrong label that is on a food container and that goes by somebody and they don't miss it, they don't notice it, that makes it into a consumer hand, that can trigger a really expensive recall where suddenly now you're going to be paying millions of dollars to get these products back into your factory, and there's all sorts of downstream health concerns. In situations like this, perhaps your human operators were missing a lot of quality issues. If you can, reduce or catch, 60% of those issues, then now you've improved quality and you've helped people out. And then, even just jumping 10 percentage points, 10 math, getting more quality, more detections. That can have really huge, I'd say, compounding results down the road. That might be all that I can share about that at this moment off the top of my head.
No, those are two amazing examples. Yeah. And definitely the faster these models are, the easier it is to do two-stage processes too. And that's true not only of RF-DETR, but generally. And with that said, I know we're coming towards the end of the hour. I did have one question, and maybe Matvei, then Isaac, you can go for this in that order. How does it feel having RF-DETR segmentation in the world?
Feels great. You see that? That gap is not present on the graph. But that gap is, you can look at it before going to bed and you'll have a good sleep.
Amazing. Isaac.
I like it. I think it's cool. I feel like with the detectors, there's a more crowded space, and this question has come up a couple of times. Like, for object detectors, there's YOLOs and there are the DETRs, and then RF-DETR is a DETR that improves on them, not always by a huge margin, but it's consistent improvement on standard data sets like GoGo. For the segmentation models, there aren't really great DETRs in that space. I mean, so there's fast inst, which is like close to the latency. It doesn't support TensorRT, so you can't really get it within that latency, but its flops count is like similar to our like the medium here. So maybe it's like, but we're 10 map better than that. The best DETRs for segmentation in my mind are all slow, like Mask Dino and CoDETR. They're phenomenal papers, but they don't target this low latency use case, and they also don't have pipelining such that you can actually use like the real compilers to get to this point. So building this segmentation model that's DETR based, that gets you to the nice compilers and everything such that you can get into this latency domain is really cool. And I like the fact that it was more of a missing niche than there was for detection. So it's very nice to see that manifest in the world. I feel like the marginal improvement is larger, and I like that.
Absolutely. Yeah, thank you so much for that summary. And yeah, this continues in the work we're doing on these really kind of small, real-time supervised functioning models that really interest Roboflow. We want people to get the best in, whether it be finding consumer packaged goods on an assembly line or detecting cracks in drywall. So with that said, thank you everyone so much. And thank you, Patrick, Matvei, Isaac, for taking an hour to chat all about RF-DETR and machine learning, and going all the way from the high level all the way to optimizations pertains for RT. We have these webinars weekly. There'll be a variant of this available on YouTube at some point in the future. And so please look out for that. We have other videos too covering RF-DETR at launch. We've got that interview with Almond, and we've got other cool, useful pieces of vision out in the wild that you can take a look at there, youtube.com/Roboflow. And yes, join us next week. Thank you everyone so much.